In this reaction, we formed the most stable radical possible. We typically don't learn very many radical reactions in organic chemistry, but one of the most important ones is the radical hydrohalogenation reaction. Before I talk about that, though, I want to step back a little bit and talk about a regular hydrohalogenation reaction. This is something you've likely learned in your alkenes chapter. If you need a refresher, I've got a video on it down below. When we start with an alkene, we add a hydrogen halide to form a carbocation. Maybe that carbocation rearranges, the halide attacks, and we get our hydrohalogenation process. We call it the Markovnikov process. But let me ask you a different question. What if this wasn't the product that I wanted? What if, starting with the same starting material, I wanted a slightly different product? What if I wanted the product where the bromine was attached out here? I can't do that with regular HBr because it goes through the Markovnikov process. If I want to do this, I'm going to have to change the reagents somehow to get the bromine to be in a different place, even though I'm starting with exactly the same starting material. To do that, we use the radical hydrohalogenation. So the net reaction for the radical hydrohalogenation is some kind of alkene. We react with HBr and peroxides, talk about that in a second, to form the Anti-Markovnikov hydrohalogenation product. Notice a couple of differences between the radical hydrohalogenation and the traditional hydrohalogenation. We have this extra reagent, hydrogen peroxide, so that must be important. We'll talk about that in a few minutes. And notice the position of the bromine. The bromine is attached to the less substituted side of the former alkene. With the traditional Markovnikov process, the bromine is attached to the more substituted side and maybe even goes through carbocation rearrangement. We call this an anti-Markovnikov process, and that's fine. You can call it an anti-Markovnikov process. But as we go through the mechanism, I want to see if you can figure out why I don't really care for the term anti-Markovnikov. We'll talk about that as we go through the mechanism. Before we do, here are a few notes for this reaction. This is a radical mechanism, so it'll go through the initiation, propagation, termination sequence. I have a video on generic radical mechanisms if you need some refresher on that. This traditionally only works with HBr. Sometimes when we add halogens, we can use bromine or chlorine or iodine. This one traditionally only works with HBr. Again, we call this an anti-Markovnikov process. I put it in quotes. I don't really care for that term, but if you want to call it that, it's fine. I call it that too sometimes. This reaction differs a little bit in that it has two initiation steps. Okay, let's move on to the mechanism. In the initiation sequence, our goal is to form the key propagating radical, which in this reaction will be Br dot. I can't break the HBr bond. That bond is a little bit too strong. When we do initiation steps, the first initiation step almost always targets the weakest bond. And that bond is typically almost always between two hetero atoms. Oxygen-oxygen, bromine-bromine, something like that. Here we have an oxygen-oxygen bond. So our first initiation sequence, we will homolytically cleave the oxygen-oxygen bond to form two hydroxyl radicals. These two hydroxyl radicals can then react with our HBr in a second initiation step to abstract a hydrogen atom from HBr. We're going to form a new oxygen-hydrogen bond. We need 2 electrons for that bond. Where can we get those electrons? We can get 1 electron from OH dot and 1 electron from the HBr bond. Breaking the HBr bond, 1 electron forms the other half of the bond to form water as the product. When we break this bond, we need to account for the movement of both electrons. The other electron will deposit locally onto Br to form Br dot. So we get our key propagating radical Br dot and also water as a byproduct. These are the initiation steps for this reaction. The propagation sequence is our main product forming sequence in radical reactions. Whatever key propagating radical we start with, we need to form again at the end of the propagation sequence so we can circle back and do a chain reaction and continue over and over again to form the bulk of our product. The first propagation step is alkene addition. We will add Br dot across the alkene. We'll need 2 electrons to form a carbon-bromine bond. We'll get 1 of those electrons from Br dot and 1 of those electrons from half of the pi bond. This will form a new carbon-bromine bond between carbon-4 and bromine. When we break a bond, we need to account for both electrons in that bond, so the other electron will be deposited locally onto carbon number 3 as a new radical. We'll end up with a new radical on carbon number 3 and a new carbon-bromine bond with carbon number 4. This is the first propagation step for this reaction. And I want you to notice something about this reaction. Notice when we did this, we formed the radical on carbon number 3. Why do we do that? Why not on carbon number 4? Well, because carbon number 3 is a secondary carbon, the radical will be most stable on a secondary carbon and less stable on the primary carbon. When we look at our traditional hydrohalogenation, the first step, we react to form the most stable carbocation possible. That's what it means to be Markovnikov's rule. In this reaction, we formed the most stable radical possible. There's really not a lot of difference, stability-wise, between the traditional hydrohalogenation and the radical hydrohalogenation. Sure, the cool group gets attached to the less substituted side, But in this first propagation step, we form the most stable radical intermediate, just like in the first step of the hydrohalogenation, we form the most stable carbocation intermediate. This is why I don't really like calling it an anti-Markovnikov process, because it still goes through the most stable radical. We don't go through some less stable radical just to get the bromine on the less substituted side. We go through the most stable radical just like we do in the Markovnikov process. The second propagation step uses the carbon radical to abstract a hydrogen atom to form a carbon-hydrogen bond. We need 2 electrons to form that carbon-hydrogen bond. We'll get 1 electron from carbon dot and 1 electron from half of the HBr bond. When we break a bond, we account for both electrons. The remaining electron goes on to bromine to form bromine dot. This forms the major organic product of this reaction with a new carbon-hydrogen bond, and we reform Br dot as our propagating radical. This radical is the same as our initial radical. This is how we know we're completing our propagation sequence. We form more Br dot so we can start the propagation sequence over and continue the chain reaction over and over again. This is the main product forming sequence in this reaction. Every radical reaction also has termination steps. I'm not going to show them here. We can go through our traditional way of finding all termination steps. I've got a video about finding termination steps down below. We look for all of our radicals. We've got an OH radical, we've got a Br dot radical, and we've got carbon radical. So all of those can combine in all possible combinations. I'll go ahead and show them here on the slide. I don't know how important they're going to be for you. You'll need to check with your instructor about how many and what kind of termination steps you'll need to know. But these are the 7 possible termination steps, including the disproportionation. Maybe you don't even cover disproportionation in your class, that's fine. But the disproportionation step is the one that happens to form more product. One termination step always happens to form more product. It's not the key product forming step, but in this case, it is the disproportionation step for this reaction. So this is the radical hydrohalogenation. It's a lot like the traditional hydrohalogenation, except the cool group goes on the other side. It still goes through the most stable radical intermediate, just like the Markovnikov process goes through the most stable carbocation intermediate. So this is our reaction card for the radical hydrohalogenation. It's a reaction of an alkene with HBr peroxides to make an alkyl halide. This 3-phrase sentence we need to know in all possible combinations. Alkene plus HBr peroxides makes an alkyl halide. HBr peroxides turns an alkene into an alkyl halide, and an alkyl halide is made by reacting an alkene with HBr peroxides. Got a whole video on 3-phrase sentences as a study habit down below. This only works for HBr. It needs an alkene starting material, but notice that alkene disappears in the product. That will help you contrast it with other radical reactions you're going to learn. This goes through the radical intermediate. Some tags for this reaction: it is a regioselective reaction. It forms the anti-Markovnikov product, even though, as we talked about, it goes through the most stable radical intermediate. It is non-stereoselective. Should we form a stereocenter in the product, we will get a mixture of stereoisomers. And it's redox neutral. Both the starting material and the product are at the 1 CZ bond oxidation level. I have a separate video on redox levels down below.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.